Hi, everybody. My name's Todd, and I'm up here with Matthew, and we're going to talk about graph databases on AWS. First off, thank you very much for coming to the session. I hope everybody had a really awesome party last night, and I really appreciate you sticking around to the end of the conference. Cool. Yeah, so first off, who are we, and why should you even care? So my name's Todd, like I said, and I'm part of the solution architect team for partners in Europe. And my team is really focused on making sure that partners are successful on the AWS platform. I think Matthew will discuss his background when we get to handing over to him, but it's really cool that you guys are here, and thank you very much. So we're going to talk about a general overview of what graphs are in graph database technology, as well as how to deploy it on AWS. Matthew's going to talk about the Amazon fulfillment technology as a customer reference and how they did that, and as well as getting into some details about the Amazon DynamoDB plugin for Titan. So first off, what is a graph? First off, a graph is just an extension of like the tree data structure, as I'm sure everybody here is familiar with. And so a graph just has nodes and relationships, and these relationships and nodes can all have properties. So when you extend that, that becomes something called the property graph model. And when you put a database type technology on top of that, then you extend it with a query language as well. So then you can start asking questions about who's related to who and what is the interesting properties of the graph. You can also start talking about more the basic computer science questions of, so what is the necessary like bounding subset of things that are closer to another, things that are like a subset of the graph that's only connected to each other, and things like that. So this isn't the only data model that exists for graph. Other possible models that are out there are the hypergraph, something called the triple store, or the RDF, the resource description framework, popularized by W3C. It really depends on what type of standards you're really interested in, but it really comes back to what type of data you're really interested in. So when we're talking about how to model data on a graph, it really helps to, I think there's a lot of feedback, but it's probably my fault. So when it comes to graph database modeling, it really helps to first start off with what is the use case that you're trying to answer. I have a very trivial one up here that says, like, as a student, I want to know other students who know something about a subject. So then you can extend that model by first talking, by breaking it down into the nouns and the verbs, and say a student knows a subject, a student belongs to a class, and then you can start extending that in terms of the actual underlying graph of the relationships between the students, the subjects, and the knowledge. Graph fits well within the other NoSQL database concepts of document, either key value or a columnar. And it really extends that model for things that are interesting. But when you're talking about things that you need to model yourself, it really comes down to this trade-off between the cap and acid type theorems of knowing what type of consistency is necessary for your data model and your use case, and what type of availability is necessary as well. So when you're thinking about if you should use graph versus if you should use a more relational database model, it really helps to again go back to the use cases. Think about what types of queries are necessary for your underlying data. Do you need to start with an idea that says, like, I need to match everything that begins with X, or match on X? That's very well suited for graph type technology. If you need to do numerous joins do numerous like queries or transversals of a graph without doing joins, then maybe a graph database is better, because fundamentally graph databases store data as a doubly linked list where you have the data plus its adjacencies stored locally. So it comes down to, do you need to have where exactly the indices for the data actually need to reside? When you're thinking about it, also relational databases are really great for if you have to do some type of aggregation for columnar type analytics. If you have to, if it makes sense to use Cobb's theorem and really denormalize your tables and separate it out into like the third or fourth normal form, and if those really make sense for your data models, then a relational database is probably more well suited for your use case. Additionally, for some use cases, if your relational database supports recursive query support, then you might be able to utilize them as well. It really depends on how often you're going to be doing these type of graph queries and how optimized you need to think about for your use case. So there's two technologies that our customers ask us about frequently. One is Titan. So Titan fundamentally is a distributed graph. It's able to separate the storage layer from the computational layer. It leverages something called the TinkerPop framework, which I'll get into in a couple slides. When you start talking about the properties on the graph itself, then you can actually do full text queries of those using either Lucene or Solr or Elasticsearch. Additionally, it allows you to plug in the DynamoDB as the storage framework, which we'll talk about in a little bit with Matthew. Neo4j is another commonly referenced graph framework that our customers ask us about. And so Neo has a background as a JVM, and it's fundamentally like a shared nothing architecture. There's a single master that controls all the writes, and there's multiple read replicas for availability. Additionally, it easily supports like a highly available framework, and it uses Paxos as the master election for when a node fails. Neo4j also likes to use RAM for loading the database. So if you are going to be using that technology, finding an instance size on AWS that well suits your database size is pretty key. But additionally, it does have a very, very efficient spilling capability where it can utilize the local disk. Neo4j is also characterized by the use of Cypher, which is a DSL, or a domain-specific language for graph queries for them. However, they do also support Gremlin, which is the TinkerPop language. So just as an example of an AWS deployment for Neo4j, so as part of your ELB health checks, if you wanted to query using HTTP GET these different URLs for your graph, then you can select your master, or you can elect your read replicas into the different under the different ELBs just by doing a query on these and getting the 200s or the 500s. So this actually presents a very easily scalable mechanism for maintaining your graph cluster. One of the additional very interesting aspects of graph databases is like analytics over the entire graph. So if you wanted to do an analytics or an aggregation type query over the entire graph, then it's much more suitable to an OLAP instead of an OLTP type framework. So there's a couple different technologies out there that really leverage the Hadoop or the MapReduce framework. For instance, GraphX is it's analytics using Spark. So in-memory database queries, it's a functional, it's more of a declarative type programming language. where Giraffe is a graph query language or graph query methodology that uses HDFS, and it's much more like a vertex centered programming model. So I discussed TinkerPop, and so what TinkerPop is it's an Apache graph framework that describes the different levels of and the different layers of the system itself. Two of the key aspects is either Gremlin, which I talked about. It's a graph language for doing transversals, and it supports the analysis, and it searches queries on the graph itself. And there's also it's called Gremlin Structured API. It used to be called Blueprints for TinkerPop 2.0, and that's a generic graph connector framework, which ties in. It's almost like a JBDC for the graph itself, and that's the interface into the backend query and language, or the query graph engine. Sorry. When trying to decide if you actually need a graph database, it really helps to center along the use cases. Almost the canonical use case for graph is social. I know this person and this person knows this person, so I have to figure out the number of influencers or the amount of relationships that I have to another person. But some really interesting use cases come down to this fifth bullet of the sensor analysis. Yesterday, the gentleman from BMW talked about the connected car. So if you wanted to maybe think about if in a connected car I have an incident, or I see a pothole, or I have a blown out tire, and I need to broadcast that information to all the cars that are connected to me within X meters or X feet. Graph databases actually translate really well into a geospatial type construct, because R trees lend themselves really well into a graph database construct. So if you wanted to say, like, use a bounding box or describe a polygon around a sensor, graph transversals actually are really well suited for that. Just as an example of one of the use cases, one of the very common things for say a shopping website, you talk about, like, I'm looking at this, so I want to be able to present to the user, people who looked at this also bought that. That is really well suited for hitting like a graph database to find the relationships between people who viewed an item from this particular channel. However, if you wanted to do maybe like a weekly or nightly newsletter and to send that out to your customers that says, hey, by the way, something you looked at just changed, or price dropped, or we now have a new feature, that'd be more suitable for more of an OLAP type query. So in this very trivial example, you would extract the information from the Neo4j cluster using something called Maze Runner, which would take out a subset of the graph, load it into Elastic MapReduce, which supports Spark, and then maybe GraphX to do a nightly amalgamation on the entire, or aggregation on top of the entire graph to send out a large newsletter to all your users. So at this time, I've kind of covered the generics and the basics of graph technologies and graph databases on AWS. I'd like to hand it over to Matthew, who's going to talk about a really interesting customer example.
Great.
Thank you.
Thank you very much. Hello, everybody. My name is Matthew Souders. I'm a senior software engineer in Amazon Operations Technology. I've been with Amazon 3 years now. When I started in Amazon Fulfillment Technologies, and that's the space that I'm about to talk about. I started on the receive team, and after that, after about a year, we started looking at automating as much of the inbound space as possible. And with that, let me explain a little bit about inbound logistics. So sellers want to sell stuff on Amazon.com. And to do that, they send us their product that goes into our fulfillment centers, where a receiver will scan the products they sent, count them, then that gets sent down to stowers. Stowers scan the products, put it into bins. Those are the containers where it's kept on the shelves until people purchase it on Amazon.com and it's sent out to them. So what are some of the data problems that are involved in that? So anytime you have a touch point, that's an opportunity, particularly if you have a human counting it, for error, right? So you have miscounts either at the seller, at the receiver, at the stower, right? And when there's a miscount, somebody is not going to be paid or paid too much, right? Those are bad things on both sides. So how have we handled this in the past? So for a very long time, what we had is all of our tools emitted events, and those events were recorded into a database somewhere. And it basically said this item was added here, this item was moved from here to here, this item was deleted from this place. And so people would look into these logs, this database, and so try to manually do this trace and follow the searches, but it's incredibly difficult. It's also incredibly error-prone. Another approach that's taken is to have unique identifiers. So if you can have a unique barcode on every single product, then there's absolutely no need to try to find where it came from, because you can just look up directly into an index and be able to find all the history for that given product. However, that's insanely expensive at Amazon scale, because we deal with millions and millions of items, and each sticker costs money, right? It's also impractical for Amazon purposes, because we sell everything from very little tiny things, like, I don't know, earbuds or something like that, to very, very large things, like, I don't know, a canoe, right? And so, like, how do you put, like, a standard sticker on all those varying size products, right? So it's impractical for some items. So this is what we came up with. We took that same event model that was created by all of our tools that said these items are added here, these items are moved from here to here, and we created this graph that's effectively able to trace our inventory throughout our fulfillment network. So these blue rectangles represent the events themselves. The red circles represent the containers that they're moved into or moved out of. And then you see some other things that represent whenever we're moving product from one fulfillment center to another fulfillment center, we want to be able to trace it back all the way to the origin. So we have two main query patterns here. We want to be able to identify, for a given box that somebody sends us, what happened to that box after we received it. And that's incredibly hard to answer, because each of the products that are in that box, they don't have unique identifiers. They have a SKU, or a stock keeping unit, right, that's generic across many sellers. And so we want to be able to know exactly who sent, for an exact box that somebody sent us, exactly what we ended up doing with it. If there were more items than they said that would be in the box, less items than they said that would be in the box. And so the other querying pattern is whenever we get to a stow, we want to put it onto a bin, and we identify that there is a miscount. So we're expecting 10 items, and we only find 9, or we find 11. And so we want to be able to trace back to the origin, know what purchase order we received it against, and adjust it accordingly so we pay the correct amount. So there's a couple of options, obviously, in trying to develop the storage model for this. So some of the ones that we went through is, okay, so can we use a traditional relational data store? Should we use a NoSQL store like DynamoDB? For the relational store, we knew that not only was our volume incredibly high to start with, but they would just keep growing as time goes on, because Amazon is growing incredibly fast. And we didn't want to have to keep vertically scaling our storage solution. Another common problem with relational databases for these graph-type models is they generally perform joins in order to find the traversal. So you have to join after join after join, depending on how many hops you have to do. And so we knew that the joining mechanism would be very expensive. And finally, we required the top type of availability because we're running around the world 24/7, and we don't want any interruptions to our operations process. So why not use DynamoDB directly? So we didn't want to use DynamoDB directly because what we would effectively build is a graph. So if there's already an existing graph API, then we can just use that and not have to try to model it ourselves and reinvent the wheel. So why did we want to model it as a graph in the first place? So there's no way to index for a single lookup to know exactly all the events that we need, right? Because these events, they come in distributed over time. We generally we're dealing with mostly the middle events, right? So the beginning and the end, they only happen much rarer than the movements in the middle. And so all of those ones in the middle, how do we know which one we have to associate with? We don't know how to associate those to all the given intermediate boxes, right? The cartons, or stows for that matter. And so we need to also be able to handle out-of-order messaging, right? So we need to be able to insert into the middle, or if we received a message that was for a stow later, we need to be able to insert a movement that we found earlier into the correct place in the graph. And also graphs provide a simple mental model. And what do I mean by that? I mean, most computer science programs, they go over what a directed graph is. So everybody's on the team is already familiar with it. They're already familiar with common traversal concepts like breadth first search, depth first search, those types of things. And so it already, everybody's already trained in how do you navigate a data structure like this. So our next topic is how did we come to Titan as the implementation to go with? So there's lots of graph database options. And so the first thing that we knew is because there's so many options and we were already kind of unfamiliar with most of them, we wanted to delay as many choices as we had to, right? And so we started with TinkerPop. And we said, okay, there's lots of these graph databases that implement the TinkerPop framework. And so let's start with that. Let's just make the assumption that we're going to use one of these graph databases that implement TinkerPop. What Titan does is it abstracts away the storage layer. So we get to delay even that decision. That is, it has this plugin layer that allows you to use multiple different storage backends based on your needs. So for instance, it has BerkeleyDB, HBase, Cassandra, and now DynamoDB. So what that allows us to do is experiment, right? So we quickly ruled out BerkeleyDB because Titan, the recommended max size for that is something like 5 million. And we knew we would be way, way beyond 5 million vertices very, very quickly. HBase, most of our team wasn't familiar with it, and they have certain additional restrictions like keeping a Hadoop cluster, keeping, it also has a single point of failure in the name nodes. And so it was also much slower than the Cassandra implementation. So we also quickly identified that as one that we weren't going to pursue further. Next, we moved to Cassandra. And so invested heavily into an experiment implementing this graph database on Cassandra. And we went with it because Cassandra is highly available, had the existing Titan implementation, which is already pretty fast. We're able to use the EC2 snitch, which basically defines your EC2 topology to Cassandra so it knows how to appropriately replicate your nodes. So in the event of a AZ failure, for instance, you don't lose all the information for that are in that ring. And we also used a random partitioner, so the load would be evenly distributed. So the lessons learned while working with Cassandra is, one, no one on our team to start with had previous experience working on Cassandra, managing a Cassandra cluster. And it's a full-time job at the level that we were operating at. Cassandra has tons of tuning that's required. It took us several months to do the tuning for Cassandra for our particular operation. And even then, in our auto-scaling groups, if a host goes down, or for whatever reason, Amazon decides that that one of our hosts needs to be replaced, we had several issues in the automatic replacement of nodes back into the Cassandra cluster. And so for a long time, we had to manually swap nodes in and out. It's a big operational overhead. So what we eventually came up with, finally, Cassandra doesn't handle deleting like all your nodes that were created before a certain point, right? So it doesn't like to be handled like a queue. So what happens is that Cassandra does what's called tombstoning. So it doesn't actually, when you tell it to delete a node, it doesn't actually delete it. It tombstones it, and then it does a form of garbage collection. So we had this massive outage that was because it was trying to delete too much, which flooded some of the hosts, which put pressure onto other hosts, which then killed them, and then boom, everything's out. So what we ended up doing was we ran two separate key spaces simultaneously, and then just we switched over who was the master and who was the slave. After a certain point, we were confident that the new one was okay. We would delete the old one, rebuild it over a period of time, switch back over, delete the old one. So that way we would only keep however much data we needed at a given time. So because we had all this operational overhead, we didn't want to continue that. We thought, hey, we know another NoSQL database that doesn't require us to do all this cluster management. DynamoDB is massively scalable. We didn't want to have all these crazy tuning options. We just wanted a few. DynamoDB allows us, we need more write, we need more read. And so the tuning on that is very simple. And the team is already familiar with DynamoDB, the programming model, all the benefits that goes to it. However, we realized that it was risky because there was no pre-existing Titan implementation, that we were going to do this ourselves. So this is what we ended up coming up with as far as the architecture goes. So we have our inventory system that emits these inventory move events. Those are that to SNS, that feeds a SQSQ. That we have our inventory notification graph populator. It reads all these events. It creates the appropriate vertices and edges. If there's a failure, it can always just throw back the event, process it later, fix all the nodes. And that all feeds into DynamoDB. On the other side, we have some clients which know how to query using our ING query service that abstracts away all the details of how Titan is implemented into DynamoDB. So what we started with was what we call the single item data model in DynamoDB. So what this does is it takes the Titan abstraction in the plugin layer, and it takes a given vertex, and it uses that as the hash key. And each of the attributes, it corresponds to a given DynamoDB attribute. So it's a dynamically named attribute in DynamoDB based off of what Titan tells us the attribute names are. So it basically stores all those values in a given row. The only problem with that for us was the DynamoDB's item cap on size. So DynamoDB has a 400 kilobyte max item size, and so that would limit us in a couple of different aspects. So one is the total number of properties a given item might have. Another would be the total number of out edges or in edges for a given vertex. And so we had to deal with our own supernodes. Supernodes is a common graph database problem. That is, you have some nodes which have many, many, many edges in and out of. So for instance, our containers, we're going to have lots of different inventory events for a given container. So this didn't work with us as we started to scale, so we came up with a second model. And that's what we call the multi-item data model. So this works actually very similar to the way the Cassandra implementation works, in that the vertex has this given hash key, each attribute is used as the range key, and then we have a value column as well. And so what we're able to do is, when we're given a range query from Titan, we're able to translate that into a DynamoDB range query. So we're able to return just the items that we need, hand that back off to Titan, and process further. So this gets us away from many of the stumbling blocks that we had from Titan as far as the scaling goes for a given vertex or edge for that matter. Okay, so DynamoDB, how does it scale? So our graph that we're running has close to 100 billion vertices. So it's very big. It's terabytes of data. And all of that, while we've been building this and continually building it, has come without a corresponding increase in latency for these queries. That's the nice thing about graphs, is that they're bound based off of what your query parameters are. That is, in our case, it's the max depth that we're going to query. That defines how many hops we're going to have. Whereas a database, if you were going to be doing these joins, it's going to grow much more rapidly based off of the entire size of the graph. Okay, so some of the lessons learned in DynamoDB. One of the features that came out in Titan 0.5 was this ability to use partition graphs. That's a very good feature. As you have a very large graph, it's highly recommended to use that particular feature to speed up your querying a lot. So in our case, as I mentioned in the Cassandra, is that we wanted to be able to drop old data, right? So what we did in this particular case with DynamoDB, our implementation is we'll run a graph for whatever acceptable time span we've decided. Then we'll run a separate graph when the time horizon is met. And for the events that are created, the edges that need to be created that span the two, we'll create what we call proxy vertices that reference the other graph, right? So for a very short period of time, we'll have 2 graph queries that will go across both. And then we'll continue on in a single graph model for however long. That does provide some nice features in that we can take a certain time span of the graph and we can serialize it, we can put it out to S3, and then later do whatever kind of analysis, which basically means we get to keep around the entire graph forever. And finally, that we've been able to achieve performance at scale without all of the overhead incurred by running our own cluster with DynamoDB. So you might be asking yourself, how do I get started with the DynamoDB plugin for Titan? So we've released this through AWS Labs in our GitHub repository, so you can go and download that. You can test around on your own local box, on your own local dev box by using the DynamoDB local implementation. DynamoDB local basically implements the DynamoDB API, but you're able to run it on your machine for dev testing. This is really nice to get up and started very fast. We also provided a CloudFormation template. So if you want to also very quickly put this into production, you can set up the environments that you need very quickly and get started with it against a production DynamoDB. So I'm not going to read through all this. I'm sure you're all thankful for that. So this is just a bunch of references for you to learn more. We'll have these slides available for you to access. It's several books on graphs, graph databases, as well as some of the blog posts that we've done on the DynamoDB plugin for Titan. So if any of this was interested to you if you are interested in this, I just want to make a quick mention. We are hiring. And with that, I'll hand it over to Todd.
Cool. Yep. So I think this awesome. Thank you, Matthew. So like we said, thank you very much for your attention to this talk. We're absolutely interested in if you have any questions or if you want to come up to us and maybe talk with maybe how like AWS can help you out with your graph database problems, and also any type of use cases that you might have running graph databases on AWS. So I think we might have a couple time for questions. Not sure how the logistics works, but happy to entertain any questions right now, or you can just come up and talk with us. Thank you.